Okay, so let's start. So this is the first class of the multivariable calculus on this semester. Let me summarize what we are going to learn in this course. So look at this title. The word multivariable calculus means that we're going to study calculus on multivariable function. So basically the calculus is study on differentiation and integration. So last semester we studied on calculus on single variable function, which means that the function contains only one dependent variable and one independent variable. This semester it's a multivariable calculus, so we are going to study on differentiation and integration on multivariable function. And multivariable function means that it contains several independent variable or possibly also several dependent variable. So the general question is, how do we take a differentiation? How do we take a differential of multivariable function? For example, if you have a function of two variable, then it means that you need two variable at the same time to determine this independent variable number z. So how do we define differentiation of two variable functions, or how do we define an integration on two variable functions? So these are the general questions that we're going to ask and answer in this semester. Okay. Okay, yeah. So to start, let's define the vector first. I will explain later why we are starting from the vector when we are going to study the multivariable calculus. So vector is an n-tuple of real number. This is the very basic definition. Maybe it's not the same definition when you learn the vector in the linear algebra, but just simply put, a vector is some collection of n real numbers, and it requires two operations. One is the sum and the other is the scalar multiplication. So if you have two vectors, for example, if you have vector A and another vector B with the same number of elements, with n real numbers, then you can add these two vectors, which is another vector whose coordinates are the sum of coordinates of each places. And another operation is scalar multiplication, which means that if you take any real number, it could be 0 or negative, we can define another vector called k times a, which becomes another vector whose coordinates are k times a1 to k times an. So basically, if you take a vector sum, it's if you represent your vector as an arrow in n-dimensional space, vector sum means the composition of two vectors, and scalar multiplication means that it's a dilation of vector, meaning that you stretch your vector to the length, stretch your length of the vector by factor k. And if you collect all the n-dimensional vectors, we call it n-dimensional vector space, and we usually denote it by Rn. I want to make a remark that usually the Rn is also used for the n-dimensional space, not the vector space. So there's a big difference between vector space and just the space. Vector space is a collection of vectors, and these vectors requires vector sum and scalar multiplication operation. But just the space is the set of points, and points are also represented by n number of real numbers, but points doesn't require the operations. You cannot add 2 points, or you cannot multiply the points by another scalar factors. Okay, so Rn is also used for n-dimensional vector space and n-dimensional space. If the notation is confusing at some context, we have to specify this means the vector space or this means the space. So if it comes up, I will clarify what this Rn means. So here's an example. So let me look at the 3-dimensional space. So this is just the space, not the vector space. And let's call this O as the origin, 0, 0, 0. And let's pick a random point P whose coordinates are A1, A2, A3. So these are points. So these points are lying in just space, okay? Now I'm going to make a position vector out of these 2 points. So vector from 0 to P is represented by this notation OP arrow, and also has the triple of A1, A2, A3. So basically these 2 notation looks the same, but it represents 2 different objects. The first one, this one represent the coordinates of point. The below one, this one represent the coordinates of vectors. Okay. Sometimes the coordinates of vectors are represented by left angle and right angle. So A1, A2, A3 angle bracket is represented by this arrow vector. You can differentiate your notation by using different notation, but it really doesn't matter, and book doesn't use this angle bracket, so I'm going to use the parenthesis. And if you take the scalar multiplication on a position vector, it's a dilation. You just stretch your vector. And vector sum of two position vectors are superposition, meaning that you're taking diagonal vectors on parallelogram made by these 2 vectors. So let's say we have OP here and we have OQ here, then here is R, and this vector is represented by OR. So R is simply a point whose coordinates are sum of coordinates of P and Q, where Q is here and P is here, and this is the origin. And therefore we can define a sum of 2 position vector in this way. So if you take the sum of OP and OQ, this is OR, or you can redefine your vector sum as OP plus PR, where PR is this vector. This is PR vectors. So you can either add these 2 vectors. Let me use another color here. So you can either add these 2 vectors. Add these 2 vectors, or you can add OP and PR to get the same OR vector. Okay. All right, so let me talk about some example of multivariable function. An example is a parametrization of a curve. So curve is simply curve is a one-dimensional thing which lies on n-dimensional space. For example, if you have 2-dimensional plane, then the curve is a geometric object of one-dimensional geometric object, and a parametrization of curve is a set of function which represents the coordinate functions of a point lying in the curve. So for example, this is our curve C. So C is nothing but a collection of points in the plane. But I want to specify a point lying in this curve. For example, let's say P lies in C, and I want to find out the coordinate of P in terms of parameter T. So when T moves from one end of interval to the another end of interval, the coordinate of P changes. Therefore, the two coordinates x and y of the point P is also the function of parameter T. So in the formal way, I can write my C as a function from interval to a point, a set of points, or entire set R2. So this is the two-dimensional space, not vector space, okay? And this is the open interval. So epsilon is positive numbers. Usually epsilon means the small positive numbers. And this is a function. So if I pick any points lying in minus epsilon to epsilon, then I get a coordinate in R2. So I can rewrite that function in specifically Ct equals to the point coordinate of point xt comma yt. So this is the one example of multivariable function. So we have one independent variable t. So t is independent variable. And we have dependent variable, which is x and y. So I used x and y as a name of functions of coordinates, but also I can use it as a dependent variable because x and y are determined by the independent variable t through this function xt and yt. So xy is dependent variable. So we have two dependent variables, so that fits the definition of multivariable function. We have two variable in the dependent side. So when you have this parameterization, I can take a differential of this parameterization function called c prime t, and simply we define, so this is a definition of c prime t as point, or it's actually a vector. It looks like a point, consists of x prime and y prime. So x and y are a single variable function. X is determined by one variable parameter t, okay, and it determines one value x, right? And y is also. So I can define the derivative of single variable function as we did in the previous semester. So this is well defined. And what I get as c prime t is a collection of ordered collection of x prime t and y prime t. And now we are going to call this as a velocity vector of parameterization c, not a point. Okay. So when I write ct, this is a point. This represents the coordinate of point. But when I write c prime t, this is the vector, meaning that it's the velocity of a point. So when you use word velocity, you need the parameter of time. So in this case, t is represented as time. Okay. And c prime t also not only measures the speed, it also measures the direction. So it moves instantaneously to the direction of x prime and y prime, which means that it moves to the x direction as in the speed of x prime, and it moves to the y direction of speed of y prime. So if you take a composition, you get the actual direction of c prime. Okay. You can generalize this idea to the parameterization of curve inside three-dimensional space, or four-dimensional or five-dimensional, in general n-dimensional space. But usually we will talk about up to three-dimensional space. So let me look another example. So here's a typo So R3. So this is R. Okay. So let's say our Rn is set of all n-dimensional. Sorry, so n-dimensional point. So typo. So Rn is an n-dimensional space, which means that it contains entire n-dimensional points. I want to define a function comes from R2 to R3. So which means that if I pick a point in R2, which you represent by two values called u and v, I get three-dimensional point represented by three values, x and y and z. So each of value x and y, z are determined by u and v simultaneously. So you need both u and v to determine x or y or z. Okay. So this is another example of multivariable function. We have two independent variable and three dependent variable. And also these x and y and z are also examples of two multivariable function because it requires two independent variables. Although x, y, z have only one dependent variable, it's still multivariable function. So this is the most general form of multivariable function that we're going to look at in this semester as a specific example. And usually it represents a surface in three-dimensional space. So let me rewrite this as a remark. So this function usually I'm sorry, let me rewrite that in this way. So the graph, I didn't define what graph of the multivariable function is yet, but the graph of f is a surface. So I didn't define what surface is yet, but you can just imagine the surface inside of three-dimensional space, like sphere or cylinder, something like that. So surface in three-dimensional space. So this is the typical. This will be the typical example that when we talk about integration and differentiation. Now, our title of textbook is vector calculus, but title of the lecture is multivariable calculus. So what's the difference? It's actually the same. If you take your point, something like as a vector, then you can consider your function, this function as a function sending vector to vector, right? Although this function is a function from space to space, but you can also define your function from vector space to vector space. Or suppose that this is the function of vector space to vector space, but you don't think about any vector operations like vector sum or scalar multiplication, then it really don't have any difference between functions of vector spaces or functions of spaces. So you can safely call multivariable calculus as a vector calculus because you are going to study about the multivariable functions which can be considered as a function of spaces or function of vector spaces. However, when you call a function of vector spaces, then it usually requires that function preserve the vector operations. So I advise you not to use a function is defined on a vector space in general, but I'm just saying that vector calculus is perfectly fine when you say what we are studying about in this semester. Okay, let's keep moving. So if you have any question, please stop me anytime. So we have suppose we have a vector. Okay, so A is a vector, and we can define a norm, which means the length of a vector, as a square root of sum of squares. So this is in fact called the Euclidean norm. You can define a different norm in different way, but we're not going to talk about the general norm here. So always talk about the Euclidean norm. Euclidean norm. So if you apply that into two-dimensional vectors or three-dimensional vectors, it actually measures the length of vector or length of position vector if you want. And that's a very natural concept. And we call a vector a unit vector if the length is 1. Okay. And there is a special vector called zero vector, which has no length. And this vector satisfies this equation that if you take a vector sum of zero vector to any other vectors, then it doesn't change the vector. So 0 plus a and a plus 0 is always a. And if you have a non-zero vector, then you can always normalize your vector, which means that you can set your length of vector to be 1 always by taking the denominator as the length of vector, the norm of vector a. So u has the same direction as vector a, but the length is 1. So unit vector is useful when you want to only take the direction of a vector but not care about the size of vectors. So here's an example. Suppose that you have an n-dimensional vector space and you want to pick some random vectors. Then your vector always can be decomposed as basis vectors called EI. So EI consist of 0 and 1, where only 1 at the i's position. And this is your unit vector by the definition norm of vectors, because if you take the square sum of all the entries here, there's only 1. Therefore, we have 1 as a norm of EI. And if you take any random vector a as a1 to an, then you can always decompose this as a1 e1 plus an en. So a1 times a1 is just column multiplication plus up to an en. So because I can decompose this into a1 0 plus up to 0 an, and take the scalar sum of take out this ai's out of this column multiplication here. And specifically, if you're talking about the three-dimensional vector space, our basis vector is represented by special characters I, j, k, okay, instead of e1, e2, e3. Maybe this is because of tradition in physics. So traditionally, in physics they used I, j, k, and in mathematics also use these traditions. We'll use this notation in our courses too. So because of this nature that any vector in n-dimensional space can be decomposed as a linear sum of basis vectors, we call the set of this basis vector as a basis of Rn. Okay, so there are two terminology, basis vector and basis. Basis vector is a vector, okay? Basis is a set of vectors, okay? So if you want to keep talking about the basis, then we have to talk about the rank or the dimension of vector space and so on, but this is as far as we go about the vector space, that we are only going to talk about our n-dimensional vector space, and this n-dimensional space has a basis, consists of this unit basis vectors, okay? And now let's talk about the inner product, also called the dot product, and we're going to use the dot notation. Sometimes the inner product is also represented by the bracket, that a comma b bracket is inner product, or a dot b. I'm not going to use this notation because it's so confusing sometimes. And it's defined as a sum of sum of multiple of each coordinates. So when you take a dot product between two vectors, the result is a real number, and also it requires condition that the size of two vectors must be the same, because you have to take the multiple of each coordinate. If the size are different between two vectors, then you can multiply at some point these two coordinates. And there's an important notation, an important definition, that if you have a 0 after taking dot product, then we call these two vectors are orthogonal, which means that these vectors are perpendicular. So I will talk about why this is true. So at here, we didn't say what meaning of orthogonal yet. It's just a definition here when this inner product gives 0. And here's the proposition. The inner product satisfies the following equations. So if you take the inner product of A on the sum of two vectors, you can distribute your inner product, A times B and A times C. And if you take the inner product between a vector and scalar multiple of vector, you can take out your scalar multiple outside of the inner product. And most importantly, you have an inner product of two same vectors itself, then you get the square of the norm of vectors. So if you have 0 vectors, basically it's always 0, or sometimes I can rewrite this as this one. Okay. Inner product between 0 vectors is always 0. I'm sorry, so this is not a vector, it's a 0 number. Okay. So where this vector used for? One example is that you can parameterize your line. So line is the simplest example of a curve inside of n-dimensional space. For example, let's talk about the space as a 3-dimensional space. I want to parameterize a line passing through the point P. Coordinates are x0, y0, and z0. Not only that you need a point, but also you need a direction of a line to determine what this line is. So let me specify the direction of this line. So I want to assume that my L is parallel to this vector A, A1, A2, A3. Then the parametric equation of L can be determined by LT equals to P times TA. So basically, I want to pick a point inside of line L according to the parameter T. So when T equals to 0, it's lying on the point P. So when T is moving to positive number, it moves to the direction of A. So if I take a twice of A, I get this point. And you can change your T in anywhere in positive real numbers, so I can pick any points lying inside entire this one-way direction of a line. If I take a negative value of T, I get the negative direction of A, so minus A here. So if I take twice of minus A, I get this far, and so on. So I get entire line here. Okay. So this is the easiest way to parameterize line. You can also rewrite your parameter in this way, a parametric equation, not a parametric equation, but equation of a line this way. So suppose that my LT is given by coordinate x, y, z. I'm just omitting t here. And let's rewrite the right hand side of this equation. We have x0, y0 and z0 plus ta, so ta1, ta2 and ta3. So let's rewrite this. So we have if I take this x0, y0, z0 to the left hand side, what I get is x minus x0, y minus y0, z minus z0 equals to ta1, ta2, ta3. So it means the left and right hand side both are vectors. It means that these two vectors must be the same. If you want to compare two vectors and requires that these two vectors to be same, then you need the coordinates are all the same. So you have three equations: x minus x0 equals to ta1, y minus y0 equals to ta2, and z minus z0 equals to ta3. So if you take a1, a2, and a3, assuming that these a1, a2, a3 are not 0, you can divide these numbers on the both sides so that you get this guy equals to t and these all guys equals to t. So this one only works when a1, a2, a3 are not always 0. Okay. So this is another way of defining your equation of line. Okay. So another way of defining a line is that you have 2 points passing 2 points lying on the same line L, then you can define your parameterization. Because suppose that you have P here and you have Q here, the direction of the line is now the vector PQ. Okay. So how do you get the PQ? So there must be an origin here. So OP, OQ here. So OP plus PQ must be OQ. So therefore we have PQ equals to OQ minus OP. So this is our direction vector A, and we can pick any point P or Q to be the point where line L passes through. So we basically go back to the first definition to define a parametric equation. Okay, so this is the most important theorem of vectors. So let's take two-dimensional vectors A and B, and let's say theta is the angle between A and B. So it could be the small angle or larger angle. It doesn't matter. Okay. So this, if you take the inner product of A and B, it's equal to the norm of A times norm of B times cosine theta. So there are easy way to define prove this theorem. Let me add another page here. Okay. Okay. Proof of A B equals to A B cosine theta. So we assume that these A, B, and B are two-dimensional vectors. So I can write safely RA as R times cosine theta 1, R1 times cosine theta 1 sine theta 1, B as R2 times cosine theta 2 sine theta 2, which means that A has length R1, so this length is R1, and angle is theta 1, and here is B, whose length is R2, and angle is theta 2, measured from the positive direction of X. Okay, so here's X and Y. And let's take the inner product. So A inner product B is equals to, so I can distribute this R1 and R2 inside of these coordinate functions. So I can take the first coordinates of A and B so that I get R1, R2, cosine theta 1, cosine theta 2, and second coordinate R1, R2, sine theta 1, sine theta 2. So R1, R2 are common, so I get R1, R2 of cosine theta 1, cosine theta 2, and sine theta 1, sine theta 2. and there is a formula that this is equals to cosine theta 2 minus theta 1, or you can rewrite this as a set r1 r2 cosine theta 1 minus theta 2. Because cosine is an even function, it doesn't matter. Okay, so r1 is the length of A. Okay, therefore this is norm of A, and r2 is length of B, and the difference between theta 1 and theta 2 is the angle measured from A to B or B to A. So therefore we have cosine theta. So this is a geometric meaning of inner product. So whenever we have remark theta equals to pi over 2, then this A, B is equals, and this means that A, B are perpendicular. Okay. So perpendicular, this means same as orthogonal. Okay. So that's our theorem. And now we can generalize this to not only two-dimensional vectors but also n-dimensional vectors. Before we actually generalize to n-dimensional vectors, let's talk about three-dimensional vectors. So if you pick any two three-dimensional vectors, it must be lying on the same plane. Okay, so let's say we have three-dimensional vector space. Let's say we take the position vectors here. So we have A and B. So there must be a plane P passing through the origin O, which contains this vector A and B. There must be a plane P containing O, containing A and B. Now, although A, B are three-dimensional vectors, if you just think about the plane P, A, B can be considered as two-dimensional vectors inside of P, right? So there must be an angle between A and B inside of P, and everything works fine as long as you stay in the plane P, because that's a two-dimensional space. You can apply your theorem on two-dimensional space inside of the plane P. So therefore this works fine. What about n-dimensional space? Even in n-dimensional space, even though I cannot draw it, if you take any two vectors, as long as these two vectors are not the same direction, then you can always pick a plane P, even in n-dimensional space. There is actually that plane is unique. Unique plane, or maybe not unique, I'm sorry, so I mean n-dimensional, maybe not unique. There is a plane containing A and B passing through 0. Okay, then even though A, B are n-dimensional space, just look at the plane P itself and consider that as two-dimensional space and A, B as a two-dimensional vectors lying in that two-dimensional space. Then everything works fine. You can define your angle between two vectors inside of that two-dimensional space, and the formula applies. So therefore, this theorem works not only two-dimensional vectors but also for any n-dimensional vectors, and you can define orthogonality of two n-dimensional vectors as long as you have an inner product. Okay, so this is another important definition, that you can project your vectors, one vector to another vector, as long as these two have different directions. So projection of A onto B is defined as another vector whose scalar multiple times the vector B. So let me rewrite that in this way. So we have b square, norm square in the denominator. So let me take this out, ab and b here. So basically I have a unit direction of vector b. So I'm getting the vector whose direction is same as the vector b, where I'm projecting my vector a to, and I'm taking some lengths on these unit vectors. So why do we get this formula, and why do we name that as the projection of a onto b? So let me explain that again here. So we have, suppose a here, and I'm sorry, so this must be b. So we have b here and a here. So it looks like it's a horizontal, but it's not. Just I'm looking at different angle of a and b, so that it looks b as an horizontal vectors. So what I'm trying to get is, when I project a perpendicularly to the vector b, I want this vector. I want a vector connecting the common starting point to the point where I get when I take projection onto b. So this is the projection of a onto b. So therefore it's obvious that it should be the same direction of b, but what matters is I want to find out the length of this vector. So let's say I want to take theta here, angle between a and b. The length of projection vector of a to b is the cosine theta of length of a, right? Now if I have a length of a vector and direction of vectors, I get everything. I can fully describe my vector. So I have length of projection vectors and direction of projection vector. The direction of projection vector is the normalization of b. So I can just multiply these two. This is a scalar number, and this is the unit vector. So I get projection of a onto b is a times cosine theta times b. Now I want to get rid of this theta, because theta is never appeared in the condition that I have a and b. Okay, but we can use the definition, a theorem of linear product. So a times b is equals to a norm b norm cosine theta. Therefore cosine theta is a times b. So I can plug in this formula here. So I get projection is equals to a times b times b. So we have inner product here. A cancels out. We get the desired formula here, right? So this is b square a times b. Okay. So once you know the projection, you can do lots of things. So first of all, let's talk about the inner product first. So we have a norm which measures the length of vectors. And what does the inner product do? Inner product measures the direction of vectors. Now it sounds weird because vectors in nature should have a direction properties, right? The vector, if you think about vector as an arrow, it must have a direction, it must have a length. But what do I mean by inner product measures the direction? So if you think about the most general form of vectors, the vector is just an element of a set having two operations which calls vector sum and scalar multiple. It's not represented by any arrows in the n-dimensional space. So only way you can measure the direction of a vector in general vector space is by inner product. For example, let's say we don't have an axis in two-dimensional space. Okay, so let's say we have a two-dimensional plane right here, and suppose that I didn't specify my axis. It could be this axis or it could be this axis. I don't know. But suppose that I have only 0 origin, and I was given by a vector A. Now I'm supposed to find out the direction of A. Now I cannot say anything here because I don't have a axis here. So only way I can get the direction of A out of here is by taking an inner product with the basis vectors. Okay, so basis vectors are not drawn here. Okay, if it's drawn here, it's obvious that where my vector A pointing at. But even though the basis vector E1, E2 are not drawn in this picture, by taking an inner product of A with the basis vector E1 and E2, I get these values. And if I omit this norm properties here, suppose that I only know the norm of the vector A, what I get is cosine value. So suppose that I have computed A inner product with E1 divided by norm of A, I get a value, and I know that this is a cosine of theta 1, where theta 1 is the angle between E1 and A1. So I know that I know theta 1 by taking the arc cosine of this value. Okay, so my E1 could be here. E1 could be here, or there are another way of finding E1 here. It could be here, right? So way you can get an theta 1 between E1 and A1 is that E1 could be on the right hand side of A1 or left hand side of A. Okay. Now, so by taking an inner product with A and E1, it's not sufficient to get the full direction of A. I need to take an inner product with E2 again. So if I take the inner product with E2, I get theta 2, which is the angle between A and E2. So so I get okay, so here we have so we have so we can E2 here. Let me say this is our theta 2. Okay. So we have origin here. So forget about the inner product with E2. When I take the inner product with E2, this theta 2 could be angle between these two vectors or these two vectors. So now we have possibility. E1 could be either this one, or E2 could be either this one. Okay. Oh, sorry, that cannot be this one. Sorry, I draw wrong here. So here is E2, same direction, but I don't want to overlap this. So E2 here, and same direction as E2. Okay. Theta 2 here. So if I measure my E1 as measure my theta 1, and I assume my E1 is here, then E2 should be appeared here. So my theta 2 must be measured this way, measured here. Okay, and let me it looks like a 45 angle degree, so it looks the same, but let me exaggerate a little bit here so that I can draw a better picture here. Let's say I have A, and let's say this is E1. Okay, so E1 could be here or here. So E2 could be here or here. Okay. So depending on the sine or theta 1 and theta 2 values, I get whether my angle lies in this coordinate system or this coordinate system. Okay. Just one inner product is not enough to find actual direction of the vector. I need two inner product between two vectors, basis vectors. Same for three-dimensional vectors. If you take the three-dimensional vector A and take the inner product with I could be everywhere. There's an infinite direction of I to find out where the I is. You need to take the inner product with J, and also you need to take the inner product K. You need three inner product. So once you've done that, once you've done all the inner product and divide by its norm, then you get cosine values and take the angle by taking arc cosine. You can find out angle between the vectors and the basis vectors. In that way, you can find out the direction of A. So if you assume that the direction of vector is not God-given, then inner product gives the direction of a vectors. Okay. All right. So now we are moving on to the part of matrix. So we were talking about the vectors. What's the relation between matrix and vectors? And first of all, what is the matrix? So matrix is nothing but a set of numbers. Now we have a row and column, not row or just column. We have two-dimensional row and column numbers. And if you arrange your numbers in rectangular way, that's called a matrix. Now, you know that the matrix here, it's simply considered, it could be considered as a vector, because when we say vector, vector is nothing but n tuple of numbers. Here we have nm tuple of numbers. So n is the number of row and m is the number of column. So here we have n rows and m columns. So we have nm tuple of real numbers. So you can consider this as a vectors too. However, if you want to call it as a vector, you need a vector sum and scalar multiplication. There is a scalar multiplication and there is a matrix multiplication and matrix addition. Here, this is a special example of matrices. Maybe we're not going to talk about this never in this semester, but maybe in linear algebra later. So we'll skip here. So if you have two matrices of the same size, which means that you have same rows and same number of columns, you can add two matrices, and the new matrix are given by this definition, that ij entry of A plus B matrix is given by the sum of ij entries of A and B. So Aij is the ith row, j's column entry of matrix A, and Bij are the same. So you get this another n by m matrix. If you take the scalar k and you want to multiply the scalar k with matrix A, then you get another vector matrix whose entry of ij is same as k times aij. Okay, so you get another matrix. So you have matrix addition and scalar multiplication of a matrix. So matrix is a vector. Or space of matrix or set of set of all n by m matrices are vector space. Okay, so on top of that, not only matrix is a vector, it also has another operation. When, oh, there's a typo. Okay, so here's a B here, B. Suppose that we have a matrix B of m row and L columns, where A is n by m matrix. Then you can define A times B, and the result is n by L matrix. Okay. So how do we define this matrix multiplication? So let's write out this rectangular form of matrices. So this is our A and this is our B. So whenever this results on n by L matrix, so we have this resulting matrix has n rows and L columns. If you want to pick ith row and jth column entry of A times B, then you need to take ith row of the first factor, so this is ith row, and jth column of second factor, and then multiply side by side. So you take Aij multiplied with B1j, okay, AI1 to B1j, AI2 to B2j, and AIM to BMJ. So you have same number of entries here, m, right? So you can multiply side by side. So that becomes, these sum becomes, so ij entry of A times B. Let's look at examples right away. So suppose that we have two matrices. This is matrix A and this is matrix B. Okay, so how do we take the matrix multiplication? First of all, A is 3 by 3 matrix and B is also 3 by 3 matrix. The resulting matrix is size of row of first factor and column of last factor. So still it's going to be a 3 by 3 matrix. So what's the first row, first column entry of A times B? You take first row of A, the first factor, and first column of the second factor, and then multiply side by side and add everything. So first column, first row is 38 times 1.19 and 25 times 1.70 plus 10 times 2.19. So you're going to compute that, and then rest of all are similar. For example, let's do the last one here. How about the third row, first column? So you take third row of the first factor and first column of the second factor. So you get 8 times 1.19 and 70 times 1.70 and 27 times 2.19. Okay, and you get 3 by 3 matrix. So this is how you take the matrix multiplication, and it's more important to understand what's the meaning of matrix multiplication. So let me give example of matrix here. Suppose Bob, Larry, and Joanna worked in a fruit store for 3 days. So this is a hypothetical situation. We have a table of names and fruits. So look at the table here. So Bob, Larry, Joanna is on the column, in this a row names of rows, and apple, orange, banana is the names of columns. So Bob apple 38 means that Bob sells apple in the price of $38. Okay, And also Bob orange 25 means that Bob sells orange in $25 and banana for $10. And Larry do the similar things. Maybe because Bob, Larry, Joanna selling these fruits in different sizes. I don't know, but anyway, there are different prices. And look at the table 2. Table 2 shows that columns of days and rows of fruits. So it means that I'm sorry, so I confused here. So this is the number of items here sold. So Bob sold apple in 38 apples, or 25 oranges, and 10 bananas, and so on. So this is number of items. Number of items sold by a person. Okay. All right, and then this means the price of items on each days. Okay. So price changes, maybe because they different. Maybe the reason why they all different have different prices because of the price changes every day. Anyway, so we have two tables, and these two tables are represented by two matrices. Okay. So when I multiply these two matrices, I get another matrix here. So what does it mean? What do I get when I take these value? So this means that 38 of apples are sold in $1.19, and 25 of what was orange is sold in $1.70, and 10 of bananas are sold in $2.19. So in total, this is the number of amount of money that Bob sold on the first day, right? Amount of dollar that Bob sold on day 1, right? Makes sense. And how about this one? This is amount of money that Bob sold on day sorry, not Bob, sorry, this is Joanna, sorry, Joanna. Joanna sold on day 1, right? So in general, if you want to take i's row and j's column of this A times B, it means that amount of dollar that person I acquired on the day J, right? So I represent the number of the label of a row, and J represent the label of a column. So the row represented by the names of persons, and the column represented by the number of days. So A times B, the IJ entries of A times B is the amount of money that person I sold on the day J, right? So if you have the same meaning of two entries in matrices, so here we have matrix A, column of matrix A represent the item, and the row of matrix B represent also the same item in the same order. Then you can have a meaning on the multiplication of two matrices A and B. And usually this is the most important thing when you think about the application of matrices, or in the machine learning when you take when you take what was it called, the name for the machine learning? So yeah, you need a back propagation to adjust your values. Then you need a matrix multiplications. Then you're going to use this meaning of multiplications of two matrices many times in machine learning. Okay. Yeah, so rest of the things that we can do on next time. So we'll finish lecture here. If you have any question, please ask anytime. So rest of the time we're going to talk about the MATLAB application, how to use the MATLAB, what we learned in this lecture.